We've talked some inverses before. Inverses undo operations when we're solving equations. Today we're going to talk about inverse functions, which are functions, equations, that if you graph them, they would reflect over the line y equals x. And the line y equals x, if you were on a coordinate plane, y equals x, if you're thinking about it in slope-intercept form, the slope-intercept is 0, the slope is 1, so it would be a line like this. So inverses perfectly reflect across that line. Now something you did in Algebra 1 to see if something was a function was called the vertical line test. And if you could draw a vertical line and it hits your graph more than once, then it's not a function. So if we're testing whether the inverse would be a function, we could do what's called the horizontal line test. If a flat line ever crosses it more than once, then the inverse would not be a function. So let's see the ones we got here. So if you look at A, and it's kind of already done, you can't draw a horizontal line and have it hit that graphed line more than once. So that means the inverse would be a function. If you look at B, if you drew a horizontal line, it hits through here more than one time, which means its inverse is not a function. So let's look at the one that we have to try. Use a horizontal line test to determine if the inverse of the relation is a function. Can you draw a flat line and have it hit this graphed line more than once? No, that's not possible. Any horizontal line you draw is just going to hit the graph once, which means its inverse is a function. Can't spell function without fun. Let's keep going. Again, we've done inverse functions before. It shouldn't be too new. Shouldn't be. But remember when you are writing the inverse equation, what we did before is you swap the x and y. You flip their places. Remember f of x is the same as y. And then you resolve it for y. So if we were to do that on this first one, the inverse of f of x equals the cube root of x plus 1. We flip x and y, so f of x, y, becomes x again. And then over here we're going to trade out the x for a y. So now we have x equals the cube root of y plus 1. And we resolve it to get y all by itself. So I see the cube root that we have to cancel out. We cancel out a cube root by cubing. So the left side will just have x cubed. The right side, the root cancels out. So we just have y plus 1. Now to get y by itself, how do you get rid of plus 1? Minus 1. So you do it to both sides. So we have x cubed minus 1 equals y. And then remember the last step for writing the inverse function is you say f inverse of x. That little, it looks like an exponent of negative 1. But it's just function and inverse notation. There it is. Let's try it again, huh? Flip-flop the x and y, so we'll have x equals y to the third minus 2. Now we're trying to get y by itself. So I'd get rid of the minus 2 by adding 2. X plus 2 equals y to the third. And now we have to get rid of that to the third power, that cube. So we undo that with its opposite, its inverse, the cube root. So we have the cube root of x plus 2 over here. You can't do anything with that. Equals, and that's done. So f inverse of x. Cool. So another way to see if they're going to give you two rules, and they'll say, are these inverses? One thing you could do is you could just take the equation, do what we just did, and see if it's the other equation. Another way that you can do that is with composite functions, similar to what we just did with composite functions here. So we're going to take one function, we're going to put it into the other function for x, simplify it as much as you can, and it needs to just come out to x. And it doesn't matter which function you put into the other. So if I were doing a here, we have 2x plus 4 and 1/2 x plus 2. Let's say I took g's function, the 1/2 x minus 4, and I put it into f's function. So we'd have f of 1/2 x minus 4 equals. And remember, this means every time in the equation we see an x, we're substituting in 1/2 x minus 4. Now there's the only x. So we're going to have 2 times this, 1/2 x plus 4. Oops, sorry, minus 4. Oh, gee whiz. Oh my gosh. 1/2 x minus 4, and then plus 4. So we need to simplify this completely, and it needs to just come out to x, nothing else. So if we distribute the 2 times 1/2 x is 1x. Hey, that's a good sign. 2 times negative 4 is negative 8, okay. Then we have that plus 4. So if we're combining our like terms, negative 8 plus 4 is negative 4. X minus 4, nothing else we can do. It needs to come out to just x, not x minus 4. So they are not inverses. And again, if you did it the other way, it's still not going to work out. So let's try b. F of x equals 1/4 x squared. G of x equals 2 root x. Doesn't matter which one we put in. Let's say we took f's function and we put it into g's. So we have g of 1/4 x squared. And we're replacing any x in the equation with 1/4 x squared. So here's what that would look like. Whoo! We got a square root of fraction. So we're going to do 2 times whatever we have here. When you square root a fraction, you square root the numerator, you square root the denominator. Square root of 1 is 1. You're welcome. That one was free. The square root of 4, though, square root of 4 is 2. Great. So we have 1/2. And then the square root of x squared is just x. 2 times 1/2, half of 2 is 1. So this comes out to 1x. Oh, that's what we need it to be. They are inverses. And it would work out both ways. If you took g's equation and substituted into f's function, it still works out to just x. That's the beauty of math. Now, I believe we're done. Oh my gosh. The time flies when you're having fun, shins. Oh.